Now the last part of the photoelectric effect that we're going to look at is going to be how do we measure these things, okay? And so we're going to look at a graphical approach and also an experimental approach. So we'll look at how we do the experiment first, and then we'll look at the graph we get from that experiment, and then how we can use that graph to find out all the information we need. Okay, so let's now say, let's look at the experiment, okay? Okay, so the things that we need to work out. So let's just put the equation here, because we know we need to be able to work out the work function. So the idea of this experiment is to calculate what is the work function of this specific material. So we want to calculate, or we want to work out the work function, okay? What we're going to do is we need to first have a what we call a vacuum photocell. Okay, so a vacuum photocell will look something like this, and it's a vacuum, and it's a vacuum because we're going to have this is our cathode that's going to release electrons. This is our anode, and if we're releasing electrons that are going to come across this gap, we don't want them to collide with anything and lose any of this kinetic energy. So we vacuum, we make it a vacuum so that there's no loss of kinetic energy. Okay, so no collisions between electrons and gas molecules, between electrons and gas, therefore no loss of kinetic energy. Okay, so that's why we need it to be a vacuum. This is our cathode, which is negatively charged. This is our anode, which is positively charged. We're going to shine some light. This light we know the frequency of. Okay, so we can choose, so the frequency is known to us. We choose what that frequency is, and we'll choose it to be a different frequency so that we can see how things are going to change. So we can alter the frequency of that. This is then going to be set up so that we can change the potential across this. So the whole circuit, you won't have to know specifically, but it will be set up so that you can change the potential across this and also measure the potential across this. Okay, so that the reason we need to do this is because what we're going to do is when electrons are released from here, they start to move across this gap with some kinetic energy, okay? Now we know the HF because we know the frequency. We're trying to work out this, so the only other thing we need is the kinetic energy. So we need to find a way to calculate the kinetic energy of these electrons, or at least the maximum kinetic energy of these electrons as they travel across this gap. So we need to figure out some way to do that. And the way we do that is that we put an ammeter here, and we measure the current. Okay, so the current is because these electrons are going to travel across this gap and they complete the circuit by being released from this this cathode. But if we change the potential so that the potential completely stops the electrons in midair, it means that we're doing work on the potential, on the electrons. Okay, so we're going to change the potential across the component in order to stop electrons from flowing, from moving across the gap. Okay, and what this is going to do is when we can actually get this, it means that the potential that we're putting across it, we're accelerating or decelerating an electron through a potential. And if you remember back to the particle physics, we said that was the definition of an electron volt, which is a unit of energy. So it means that we need to put in an amount of energy specific, so it's the charge of the electron multiplied by the potential across this gap, which we're now going to call the stopping potential. Okay, so Vs is called the stopping potential because it's the potential that we need in order to stop electrons from flowing across. Okay, so we know the charge of an electron because all electrons have the same charge, which we're basically finding the potential that we're putting across this so that the current becomes zero. Because when the current becomes zero, instead of these moving, we'll just have electrons floating in the middle. They're not actually completing the circuit. They'll be stationary in between those two cathode and anode, which means the amount of work we've done has reduced from their maximum kinetic energy to zero. And that energy that we've put in to change that is equal to the charge of the electron multiplied by the stopping potential. So that means that this amount of energy has to be equal to the maximum kinetic energy. Now this is another equation that you aren't given specifically. Just as a hint, there is an equation that looks like this in the turning point section, which is the option that you'll do. So it's also at A2. So if you don't like memorizing equations, you can look at the turning points and it tells you the equation. It's a little bit different. It says a half mv squared, so the kinetic energy is equal to EV. Okay, so this is this idea here. But this specific stopping potential then gives us the maximum kinetic energy, and then the maximum kinetic energy we now know, the energy of the photons we already knew, and so now we can work out the work function of that thing. So this is the practical application of this. We also can look at a graphical approach. So a graphical approach would be to say if our idea is HF is equal to the work function plus the kinetic energy max. The only two variables we have are going to be the kinetic energy, which can change, and the frequency that we can change. The work function and the Planck's constant are both constant values. So let's make this the subject of the formula. So let's have kinetic energy max is equal to HF minus the work function. Okay, this, if you'll notice, is in the form y equals mx plus c, and so we can have a graph that looks like this, where we have f is our x component, the maximum kinetic energy is our y component, the gradient is Planck's constant, and the y-intercept is going to be negative the work function. So what we'll actually find with experimental data is something that looks like this, roughly. Obviously, we can't have experimental data that's taking kinetic energy less than zero because we can't have negative energies. So we have to kind of trace this line back until we get to its y-intercept. This value here is minus the work function. This point here where we have this is where electrons will be emitted, but we have zero kinetic energy. This is called the threshold frequency. Okay, so the threshold frequency is the minimum frequency in order for electrons to be emitted without having kinetic energy. And the gradient of this is Planck's constant. Okay, so they'll sometimes ask you what happens, or draw a graph that would change if you had a metal with a higher work function, for example. And if we have a metal with a higher work function, it means it needs a higher frequency. So the frequency is going to go up, which is going to mean the work function is also going to increase if you were to trace it back. But the gradient has to stay the same because it's a constant value. Okay, so this is everything that we need to know on the photoelectric effect. It is quite a lot, but it is a very important effect that's going to help us to prove a lot of things. And hopefully this all makes sense. Thank you for watching.